In the last section, we were looking at a data set from Pima Indians Diabetes Database. And again, to remind you, the objective of the data set was to diagnostically predict whether or not a patient has diabetes. So we tried to construct a logistic model to predict whether or not a patient has diabetes based on two predictors. And if you recall, the predictors were BMI and glucose. And if you recall, we ended up plotting a 3D surface of glucose versus BMI versus outcome. And finally, plotted our data from the test set onto our 3D surface. But by simply looking at the visualization, it's hard to be able to tell how good of a model it is at detecting the positives, in this case, the ones, predicting whether a patient has diabetes. Another question comes to mind. How many of the positively classified are actually relevant? Do we have any misclassification when it comes to false positives or false negatives? Being able to evaluate classification models is very important, and that's what we're going to be focusing on today. So instead of looking at a logistic regression model in 3 dimensions, I'm going to try to look at it in 2 dimensions. So I'm going to simplify this logistic model and look at outcome versus glucose and outcome versus BMI. So the first logistic regression model that I'm going to be taking a look at is the outcome versus one of my predictor variables. In this case, I'm going to select BMI. Now, I've plotted my actual BMI test data from the diabetes database, and I've plotted my predicted BMI test data from the diabetes database. And I also plotted my regression model, which is a sigmoid function. As can be seen from the screen, for the most part, the predicted BMI test data matched the actual BMI test data, which you can see here, the blue and the red, and the blue and the red. But also in some instances, there was a mismatch between the actual test data and the predicted test data. So in this case, we had some true positives, true negatives. We also had some false positives and some false negatives. So in this example, if someone had a BMI of 41.5 who did not have diabetes, it was predicted that they did have diabetes based off our logistic model. So there was a misclassification in that case, since they were above that cutoff value of zero point 0.5. On the other hand, based off of our actual data, there were instances where patients had diabetes with BMI less than 40 at 30.4 or at 27, which were also misclassifications. Now let's go ahead and switch gears and look at the other logistic model of outcome versus my predictor variable for glucose. And as you can see here, we have our sigmoid function. We have also the predicted glucose test data in the black diamond. And we have also the actual glucose test data from the diabetes database. Now, if you notice right off the bat over here, we have a few less cases where there's a mismatch between actual data and predicted data. So in this case, false positives. And we have a few test cases where also at the same time, we have false negatives. The cutoff point for pi hat is 1/2, and this occurs at about a glucose value of 140 or so. Outstanding. Now the question comes up when we're looking at our logistic regression for glucose test data and BMI test data. The question that comes to mind is which one's more accurate? Which one's more sensitive? Which one's more precise? Which model should we use to diagnostically predict whether or not a patient has diabetes based on certain diagnostic measurements? If we try to plot our actual glucose test data with our actual BMI test data, while also looking at our predicted glucose test data with our predicted BMI test data, our glucose logistic regression model with our BMI logistic regression model side by side. We can visually see all the data, but it is hard to compare our classifiers without another method. Luckily, there is a way to describe the performance of a classification model on a set of test data for which the true values are known. That is where the confusion matrix comes into the limelight. One would naturally ask, what is confusion matrix? Well, in the field of machine learning and statistical classification, confusion matrix, it's a very intuitive crosstab of actual class values and predicted class values. Simply put, it is a classification method performance evaluation. So what does that really mean? Well, to evaluate the accuracy of a classification model, it really starts with summarizing the results into a couple of groups. You have the true positives, which are the observations predicted to be part of a class that are actually part of that class. You have the true negatives, which are the observations predicted not to be part of a class that are actually not part of that class. You have the false positives, which are the observations predicted to be part of a class that are actually not part of the class. Last but not least, you have the false negatives, which are the observations predicted not to be part of a class that are actually part of the class. So I went ahead and labeled my false positives and when a class 0 observation is misclassified as a class 1 observation as N01. And then I also labeled my false negatives in when a class 1 observation is misclassified as a class 0 observation. So in this case, it's an N10. So again, a confusion matrix, it's a table that allows you to visualize the performance of the classification model. And what I just described is a 2 by 2 confusion matrix in abstract terms. Now, there are other classification metrics that are shown in this figure, such as the accuracy or the prevalence or the true positive rate, false positive rate. So we're not going to be covering all of those, but we are going to be talking about a few of those. The first classification metric that I would like to delve into is the overall error rate. So what is the overall error rate? Well, it's the percentage of misclassified observations. Simply put, it's the misclassified observations divided by all the observations. To determine the overall error rate, well, you have a following formula. N10 plus N01 divided by the sum of N11 plus N10 plus N01 plus N00. Simply put, it is your false positives plus your false negatives divided by all your observations. The next metric I would like to talk about is your accuracy, which is 1 minus overall error rate. What does accuracy provide you? Well, it tells you how many instances did the model label correctly. It is a ratio of correct predictions to total predictions. Another important metric that I would like to talk about is the recall, also known as sensitivity, probability of detection, true positive rate. Simply put, it is a metric that provides the ability to correctly identify positive results. In summary, it tells us how good a test is at detecting the positives. When is that important? Well, when identifying the positives is critical. So, for example, in the event of a deadly disease or trying to predict financial default. Another metric that's important is the specificity. That is the ability to correctly identify negative results, i.e., trying to diagnose for a health condition before treatment, or you don't want to raise false alarms. And the last metric that I'd like to talk about is the precision, also known as positive predictive value. Precision provides confidence of your predicted positives. So, how many of the positively classified as positive out of all the positives? Now you can see in the formulas you have a TP, and TP stands for true positives, FN, false negatives, and these are the formulas to determine the classification metrics. And of course, the last two formulas help determine the class error rates. Now let's try to look at how a confusion matrix can be used in the context of predicting diabetes from our dataset. So I'm going to go ahead and copy and paste some code really quick that imports the necessary libraries, load the diabetes data into the diabetes data frame, and split the data into training and test sets with a 75% to 25% split. In the next part, I'm going to go ahead and copy and paste some code that you've seen before. But in this case, I'm going to build a logistic model for BMI and outcome, fitting the model according to the training data that I've split, run the model on the test data, in this case, the BMI test data, and the last part, which is new, is to generate a confusion matrix and print out a classification report. So I'm going to go ahead and run my code. And sure enough, a classification report was generated for BMI. Outstanding. Right off the bat, I can see that my precision is about 53.3%. My recall is 25.8%. My specificity is 89.2%. And my accuracy is about 68.75%, with a total of 192 observations. This is very cool. These are the classification metrics that we talked about earlier. Now, naturally, you're going to ask, well, where's that 2 by 2 confusion matrix of true positives, true negatives, false positives? Not to worry. There is a way to generate it. How? With a heat map. So I'm going to go ahead and copy and paste some code. Scroll down a little bit. And I'm going to plot my 2 by 2 confusion matrix. And voila. This shows us a 2 by 2 confusion matrix with our true negatives, true positives, false negatives, false positives. Our model predicted based on the BMI values that 46 patients would not have diabetes, where in actuality they did have diabetes. And at the same token, our model predicted that 14 patients had diabetes when they actually did not. There's a wealth of information in this confusion matrix. So I'm going to go ahead and copy and paste some code that will show you how to extract a lot of this very important information so that you're able to determine the overall error rate, the sensitivity, specificity, precision, class error rate, class 1 error rate, accuracy, and so on. So what I'm going to go ahead and do is copy and paste some code. So the first few lines are going to show my true positives, true negatives, false negatives. My true positives, again, is where my observations predicted to be part of a class that are actually part of a class, in this case, 1, 1. False positives, 0, 1, in this case, 0, 1. True negatives, 0, 0. Last but not least, false negatives, 1, 0. All right. So again, my misclassified observations is the sum of my false positives plus my false negatives, which is in this case 1, 0 and 0, 1. And of course, all my observations are the sum of all results. In this case, true positives plus true negatives plus false negative. My overall error rate is misclassified observations divided by all observations. The accuracy is 1 minus my overall error rate. If we scroll to line 20, this is the formula that will give you the class 1 error rate. Sensitivity is the observations predicted to be part of a class that are actually part of the class. So in this case, true positives divided by the sum of true positives plus false negatives. Specificity is the true negatives divided by true negatives plus false positives. And last but not least, the precision, which is true positives divided by true positives plus false positives. All right, so I'm going to go ahead and run this. And huzzah, here we go. These are the values for misclassified observations, all observations, the error rate, the accuracy, the sensitivity, specificity, precision for my BMI classification model. My recall for the classification model is low, 25%, especially when identifying the positives is crucial. So my classification model, to be able to correctly identify positive results, is not very strong, albeit having a high value of accuracy. So let's switch gears and build a logistics model based off of our glucose predictor, now that we know how to do that. So I'm going to go ahead and copy and paste some code. First, I'm going to build my logistics model trained on my glucose data, create my predictions with my glucose test data, and last part, print out a classification report. And as you can see, the values improved dramatically. So my recall jumped from 25 to about 50%. Toss of a coin. Specificity, still hovering about 89.2%. And my accuracy jumped to 76.6% from 68.8%. Seems like a much better model, especially when looking at our classification metrics. Now let's kick it up a notch and build a logistics model based off of our two predictors, glucose and BMI. So I'm going to go ahead, copy and paste some code, run it. And right away, you can see that the recall has improved from 50 to 53%, better than toss of a coin. Accuracy jumped slightly to 77.6, and my precision jumped to about 70.2%. Now, if you recall, when we were just looking at our BMI as a predictor, my precision was 53.3%. So that improved quite dramatically. That gives us confidence of our predicted positives, of how many observations were correctly classified as positives out of all the positives. Outstanding. Now, for fun, let's build our 2x2 confusion matrix. So I'm going to copy and paste the same code that I used before by plotting a heat map. This shows us our groups when it comes to true positives, true negatives, false positives, false negatives. Now I'm going to copy and paste the same code that we, again, used before to provide me the classification metrics to include my error rates. So I'm going to go ahead and run this code. And again, as you can see right away, the number of misclassified observations dropped to 43. And if you recall, that originally, that value was 60. And my class 1 and class 0 error rates also dropped considerably, which indicates to me that this classification model of two predictors is better than the first classification model that we built with the BMI predictor. And above all, this provides us the ability to perform side-by-side comparisons, especially when we're testing out multiple models to answer the question or solve a problem of how to use the data set to diagnostically predict whether or not a patient has diabetes based on certain diagnostic measurements included in the data set. These metrics allow us to see not only how accurate one model is over the other, but also allows us to be more granular on how a model does in sensitivity, specificity, and precision. Fantastic. Now, just to repeat again, confusion matrices can help with side-by-side comparison of different classification methods, but I am a very visual person. I would like to see these classification models compared side by side visually. That is where the receiver operating characteristic ROC curves come into play. So a receiver operating characteristic ROC curve is just that. It's a graphical plot that illustrates the diagnostic ability of a binary classifier system as its discrimination threshold is varied. It was first used in signal detection theory, but is now used in many other areas: radiology, medicine, natural hazards, and of course, machine learning. An ROC curve, it's a two-dimensional graph that plots the class 0 error rate on the horizontal axis and the sensitivity on the vertical axis. To simplify, I installed the plot metric library, and if you wanted more information on, you can go to pypy.org /project/plot to plot ROC curve for the logistic regression model that includes my two predictor variables. So for fun, I went ahead and copy and pasted some code using my two predictor variables and then plot a ROC curve. And here we go. This is it. This is what a ROC curve looks like. Class C error rate on the horizontal axis, sensitivity on the vertical axis. And right at the bottom, you see area equals 0.83. That's your area under curve AUC. And it is one way to summarize the performance of a model with a single number for comparison purposes. Now, just for fun, if I wanted to compare my classification model via the logistic regression with my k-nearest neighbors classification model that we did a few lectures back with a k value of 10. All that I need to do is copy and paste some code, build a k-NN classifier with a k value of 10, train my classifier on the two predictor variables, BMI and glucose, and finally plot with Plotmetric. I'm gonna go ahead and run. And right off the bat, you can see that my AUC value is 0.78. Therefore, side by side, the logistic regression model did a little bit better when it comes to ranking a classification model. The nice thing about AUC, it's a classification threshold invariant. It measures the quality of the model's predictions irrespective of what classification threshold is chosen. This is fantastic. So if I wanted to generate a plot with the two ROC curves via Plotmetric, then I'm just going to go ahead and copy and paste some code, plotting my logistic regression and my KNN classification model. And here we go. As noted, the logistic regression model did a little better than my KNN model with a k value of 10. Now, I didn't like the way this plot looked like, so I went ahead and cleaned up the code and added the other classification models that we discussed in this lecture when it comes to just looking at one predictor variable, in this case, the BMI and glucose, and generated a plot. And as you can see here, this plot compares the logistic regression models for the two predictor variables, the one predictor variable, glucose, the BMI, and my KNN model. And as you can see here, the AUC for the BMI was 0.67, for the glucose was 0.81, for the KNN, for the two predictors, it was 0.78, and the best one was the BMI and glucose via the logistic regression model. And of course, the closer the curve comes to the 45-degree diagonal of the ROC space, the less accurate the test. So typically, we want to be over here when it comes to the ROC curve, closer to a true positive rate of 1 and a false positive rate of 0. So again, the AUC is desirable because it's an aggregate measure of performance across all possible classification thresholds. AUC is scale invariant. It measures how well predictions are ranked, rather than absolute values as you saw in the beginning of the lecture. Last but not least, the AUC measures the quality of the model's predictions irrespective of what classification threshold is chosen. Absolutely fantastic. So again, the ROC curve was used to compare classification models based on completely different methods. And the area under curve was a way to summarize the performance of the models with a single number for comparison purposes. And last but not least, the AUC of the naive or random model is usually represented by the red diagonal line, which is a half. Amazing. This concludes our section on evaluating classification models.